start something now.
Yeah. Hello, and welcome to today's PSU Transportation Seminar. My name is Jason, and I will be moderating and introducing today's seminar speakers. Our Friday Transportation Seminar has been a tradition since the year 2000. These seminars are usually held live on Portland State University's urban campus, located on the ancestral homelands of the Multnomah, Cathlamet, Clackamas, Tumwater, and Watlala bands of the Chinook, the Tualatin Kalapuya, and many other indigenous nations of the Columbia River. It is important to acknowledge that we are here because of the sacrifices forced on the indigenous ancestors of this place, remember these communities, and to honor their legacy, lives, and descendants. Today, we are pleased to have Mark Haines and Jesse Stemmler. Stemmler, all right. That's 2 weeks in a row I butchered some names, sorry. Presenting the Division Transit Project. Mark Haines is an engineer too in the Intelligent Transportation Systems Group of PBOT. Mark is a technical expert on innovative applications of existing and future technology who supports connecting communities and creating safer transportation systems. Mark was the lead traffic signals and systems engineer representing the city of Portland on the Division FX project, where he helped create a first of its kind transit signal priority system. Mark is a professional engineer, a professional traffic operations engineer, and he holds a Bachelor of Science in Civil Engineering from Portland State University. Go Vikings. Jesse is the principal project manager for TriMet's 82nd Avenue Transit Project, where he oversees planning, design, and coordination efforts for the project. Previously, he served as the senior transit designer for TriMet's major projects division and as design manager for the Division Transit Project, also known as FX. Before joining TriMet, Jesse led his own urban design studio specializing in streetscapes, transportation corridors, and public space planning. He holds a Master of Landscape Architecture from the University of California at Berkeley, focusing on community design and development, as well as a Bachelor of Science in Environmental Science and a Bachelor of Arts in Spanish from Northern Arizona University. Here's a preview of some of our upcoming seminars. And for those of you who are students at PSU, here are some of the upcoming events from the Students in Transportation Planning and Engineering Student Group, also known as STEP. As an overview of today's seminar, you can expect our speaker to present for about 45 minutes, which will be followed by a Q&A session. We will be receiving questions through the Q&A feature on your Zoom control panel, and we'll ask them at the end of the presentation. If we run out of time for all of your questions, we will give our speaker the opportunity to email written responses for any questions left unanswered. We have enabled closed captioning, but you must click on the CC feature to view them. We will be recording today's webinar. It will be available on our website later today, along with the presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. With that, I will now hand it over to Mark and Jesse. Mark and Jesse. Got it.
Thank you, everyone. Thank you for PSU for hosting us today. Today, we're going to talk about our FX system and specifically FX2 division, which is Portland Region's first foray into bus rapid transit. So I'll do a little bit of background, talk a little bit about the project holistically, and then turn over to Mark as we talk about the tools that we're using on FX to have more efficient, faster travel times for our buses and improve transit in general. So first, I just want to talk before FX, pre-FX Division Street. If we could go to the next slide, please.
The slide control.
Okay, thank you. Back in 2014, early planning started as part of the high capacity transit plan coming out of Metro to look at where BRT corridors could be in the region. Division Street at the time was right up there with Max Lines in terms of ridership. It had some of the highest ridership we saw anywhere in our system. And there was a real need to improve transit, travel times, reliability, especially for those folks living in East Portland that really relied on that service to get to downtown daily needs. In terms of the corridor itself, it is a 15-mile corridor when you take into account its connection within the transit mall. It connects downtown Portland to Gresham in the east, and it is made up of 83 station platforms placed about every third of a mile along the corridor. At the time of doing this is our first BRT, and we had hoped in doing our early planning and design work for about 15 to 20% travel time when we looked at all the different tools. And I'll talk about those tools in a moment. In terms of just the overall timeline for the project, I had mentioned we had started in 2014 of the planning work. Design really started what we call project development in 2017. This was a small starts project being a project with FTA federal funding for half of the investment, which was $175 million project. So design took place over a course of about 2 years, then construction for just shy of 3 years, with service ultimately opening in September of 2022. So what does it mean when we talk about FX? What does it mean in terms of BRT for our region? For us, it means 60-foot articulated buses. I'm sure you've seen those green buses going up and down the transit mall with 3-door boarding. We have consolidated stops that I talked about. We ended up, I think, on Division, probably removing close to about half of the stops that were pre-existing on the corridor. And we really looked closely at where the highest ridership was, where are we getting most of the ramp deployments for mobility devices, where are their destinations. And we use a host of other tools, including lane dedication. We'll talk more about transit signal priority in a moment, but placing stations far side of intersections to be able to get more efficiently through those intersections, having near level platforms so riders can step on and off the bus much more quickly, having bikes on board, having in-lane stops so a bus is not having to pull out and then pull back in. So a host of tools that we use to improve service on Division. I'm going to talk for a moment here about the station designs. For FX, we knew, and Division specifically, if you know Division, there's interdivision, which is, 2-lane cross section, sometimes a turn lane, and then you get out to closer to Gresham and you get into a 5-lane cross section. And the context, the urban context, is very different. And so we knew we were operating in a lot of different contexts. And so our stations designs really needed to respond to that. And we also saw this as an opportunity to not only design for Division, but design for the region, anticipating we would do future FX in other places. And so we looked at a custom station design, shelter design that we refer to as a frames design that allowed us to really have this flexibility. So if we were right up against a building, we could look at reducing dimensions by removing some of the side wind screens, or if we had higher ridership, we could simply expand the shelter design. So we're really looking for this flexible design that could work in a myriad of contexts. And this station design we imagine to be rolled out on future FX lines as well. Also, something unique to the project was looking at different station typologies to also respond to the context. Between 82nd and 175th, there is a protected bicycle lane, and we really needed to figure out a way how to weave our stations within this constrained environment and with the protected bicycle lanes. So we ended up, after a 6 months work session, working with a lot of different partners and interests, ended up landing on what we called the shared bicycle and pedestrian platform design, which is a 4-foot step out, a 3-foot bike lane, and the station design dimension can change, but it's typically anywhere between 10, 12 feet. And so this design was really a result of a lot of work with our partners, also involving groups like the Pedestrian Advisory Committee, the Bicycle Advisory Committee, the Committee on Accessible Transit. We started in work sessions with plans, then eventually graduated to putting tape on the ground, to then saying, hey, if we're really going to do this and we're going to put this across the corridor and potentially even use it elsewhere, we need to really understand how this works in the real world. And so we ended up eventually building a full-scale mock-up out of plywood with the ability to have station elements and dimension shift and change in real time. And over a series of months, orchestrated a series of simulated testing and brought operators out and bicycles out, people in mobility devices, and we asked them to run through a simulation of how this would work and really tested it from all of those perspectives. We also asked individuals to be their baddest selves and act as if someone may not operate and use a platform how we think they may. So what does it mean if a bicycle is going the opposite direction? What does it mean if someone's walking in the bike lane? So we're testing all of those scenarios too, to make sure that if we were putting something out like this out in the street, we really understood how it operated. And so ultimately, after doing that work, we ended up landing on this design, what again we call the shared bicycle and pedestrian platform design. The expectation is that when bikes come to a station platform area and there is a bus at the station, the expectation is those bicycles stop, passengers unload and load, and then bicycles can continue. I think you can probably guess that that never happens, right? So we ended up doing, just to continue this rigor around this station design, we ended up working with PSU, Nathan McNeil and his team to really continue this rigor around this station design. Again, we really wanted to understand how this was working, and not just by doing early study design, but once it's been implemented, what does that mean? Is it working? Is it not working? Are there places to have some of these modifications? So Nathan and his team over the course of a couple years ended up doing monitoring of half a dozen station locations, eight different station locations, to understand through the use of cameras, video, what those intersections are like. And as I mentioned, no surprise, the bicyclists never stop. But what we're finding is these station environments are working quite well. We're seeing very minor conflicts between, at times, pedestrians and bicyclists, but for the most case, they're able to navigate those relationships. And in a place like Division, where it's a high crash corridor, and when we put bikes in street and we see the conflicts in that case often being deadly, this seems like a far better approach if you were to ask me. So we're going to transition over to another tool. We had mentioned just briefly transit signal priority, that ability for buses to talk to signals. And it is another place that for FX and Division, we are really looking to do something different and innovate. So I'll turn it over now to Mark to talk a little bit more about that system and how it was implemented and how it's performing on the corridor.
Thank you. Thanks all for being here today. This is going to get a little bit wonky. So if you have questions now or later, feel free. I'm always happy to help answer them as we go along. But first, I want to kind of put you in my brain space as this project was being developed. So we had this incredible opportunity to reimagine what traffic signal operations look like along a corridor. We touched 45 signals as part of this project. We really wanted to rethink what are our priorities, what are our goals. And traffic operations relies heavily on space and time, but really mostly time. And since time affects everyone a little bit differently, we wanted to center ourselves by looking at our work through some lenses. So first, as Jesse mentioned, high crash corridor. So Division is part of our high injury network. It is considered a high crash corridor. And 5 of the intersections along the corridor are also high crash intersections. So we wanted to look at our work through a lens of safety. The next lens was a lens of equity. So there are 11 high equity zones along Division, according to the PBOT equity matrix. And what that means is those are places where we really want to focus our efforts, our investments on to improve the lives and livelihood of the people, the communities that that live there in a context that's appropriate for them. And the third lens we chose to use was the PBOT modal hierarchy lens. So PBOT has a modal hierarchy where at the very top, the highest priority are people walking and rolling, then people on bikes, public transit, and then at the very bottom, private automobile use. As I said, we touched 45 signals as part of this project. So that included all new signal timing for 45 traffic signals. There were also 2 ODOT signals and I think 9 or 11 Gresham signals. As part of that, we added 18 pedestrian head starts. Those are advanced walk or LPIs. That's what PBOT calls them. At 14 locations, we exclusively phased the pedestrian movements crossing division, which means we gave them an exclusive time in the cycle to further protect their movement. We also developed a PED priority routine for all 45 signals, and that's basically if someone pushes the button, they shouldn't have to wait for their time in the cycle to get access. They push the button, they get access almost immediately. And then we'll talk about next-gen TSP also at the 45 traffic signals. So let me talk about design for a little bit, because all through this process, we were looking at design. How does that affect operations? How does that affect next-gen TSP? And how does that all work together to create a better system for people living and traveling on division? So on the left, you'll see kind of a typical intersection along division, curb type bike lanes through right turn lanes, signalized. On the right, you'll see that we started thinking about how do we add some different movements to this corridor. So we added bus lanes that became bus and right turn only lanes. And that pushed a lane to the left, a right turn lane to the left of the bike lane. And the MUTCD, for those who are familiar, says that when you put a right turn only lane to the left of a bike lane, you must separate it in time. So that added another kind of specific operation required for these intersections. So let's look at the design. So here's an example at 119th in division, where we added the bus only lane and the right turn only lane to the left of a bike lane. You can see that in the eastbound direction. And what does that look like from a signals perspective? As you view the signal mast arm, you can see there are indications now for the through movement. There's a right turn only signal, a separated bike indication. And then we also introduced this bus signal to give further clarity for the bus operators and other traffic that there's something different happening here. Now, for that signal, we did rely on the 2009 MUTCD to create a design for the bus signal. So the horizontal bar represents the red, the vertical bar represents the green, and the triangle actually flashes, and that represents the yellow indication. Here again, you can see an approach. This is at 122nd in division. And the bus just made it through. So now their signal shows a horizontal bar, which indicates red. And you see a protected right turn overlap that's happening at that time. So that was all part of the sort of design phase. These were some of the more complicated intersections, if you will. Now let's talk a little bit about operations. So here's that same intersection, 119th in division. You can see that traditional 8-phase, this would be a traditional 8-phase intersection. So our intersection timing might look something like this. And for those who haven't seen this before, imagine a vertical bar running through this rotation. And any square that vertical bar intersects, those are the movements that can go together. So you see 1 and 6 would be able to go together. And on the diagram to the left, you can see 1 and 6 would go together. So that's what it would traditionally look like. But as we add these movements in, we wanted to maintain flexibility and responsiveness to the modes that are using the intersection. So we developed some different timing. So as we add in that right turn only lane, the bus lane, and move that bike lane a little bit further to the curb, we see now we have to operate this in a little bit different way. So the overlaps now are representing different movements that add efficiency and flexibility to the intersection. Another thing that we decided to do along this corridor through a lens of safety, we decided not to run flashing yellow arrow operation. And there are some safety implications for a permissive left turn movement like that, especially considering people crossing the street. So what we did instead was we found another feature in the controller called vehicle reservice. And what this allows the controller to do is if there's a gap in oncoming traffic, we can bring up the protected left turn again in that same cycle, providing better performance for those left turns, while still maintaining the safety and separation for people crossing the street. Now, all of these operation decisions took new technology. So about 5 or 6 years ago, we came up with a new standard for our vehicle detection. It used to be inductive loops placed around the intersection. Now we can capture 64 detection zones with just 8 radar detectors. And this has implications for paving activity and other things, but one of the great benefits here is we get a ton of data now about how our signal system is operating. So our radar detectors allow us to get not just the operational needs of the intersection taken care of, but we can also get a ton of data about it, about how the intersection is responding to the different needs of the intersection. And another thing that we did recently, I guess 5 or 6 years ago, was update the controller. So now this is like the computer that we program to take care of the traffic signal itself. We've gone to an advanced transportation controller. It's now accessible through our network. So we can get something that looks kind of like the top right screen. It shows a lot more information about how the intersection is running today. It gives us different sets of data for previous recorded splits. And it's much nicer to look at than that tiny screen that's on the controller. Another thing I want to mention here is above the controller, there's another black box that's on its side. That is the radar computer, if you will. As part of this project and previous projects, we found a way to plug that in directly to the controller to get the information digitally. And that, if you can see the racks down below, those are usually filled with pieces of hardware that we've had to maintain over the years and update. So this saves us a ton of money in maintenance in the long term. Okay, so that was kind of a warm up. Now we're going to get a little more wonky. Who's ready? Okay, so 3 of the intersections on this corridor have protected intersection elements. So protected intersection, in this case, I'm going to just talk about the piece where the cyclist movement kind of pushes further away from the intersection to make its crossing, creating additional separation between the right turn movements and the ped and bike movements that are concurrent. So with a design like this, there were a lot more movements to think about. We had to think deeply about which movements can go together. How do we continue to protect people walking and rolling through the intersection? And I just want to show you this picture of what it would look like if you were in the bike lane. So you can see all the different movements that can happen on the signal mast arm, and how actually we decided to separate the right turn only phase during the cycle with the ped and bike to further add protection. But with these design elements, even if someone decides to go on a red when they're not supposed to, this provides a little bit more separation in those movements. But as I said, this took a lot of thought. And so what we ended up doing was removing sort of the traditional numbers from the traditional phasing that we have done before. And just looking at, this is hard to see, but just looking at which movements can go together and how can they go together. And then we started building on that and figuring out, okay, if we have these movements that can go together, when in the cycle can we provide service for the bus movements? And this is sort of what we came up with. And this was before we knew who our vendor was for the next gen transit signal priority system. So we actually offer a leading, a lagging, and a third opportunity for the bus to get through the signal. And what this means is that a bus could be delayed maybe up to 40 seconds is all, if the system didn't work correctly. So worst case scenario, it's about a 40-second delay for the bus. So this was a big step in how do we get the bus through? How do we protect people walking and rolling through the intersection? And what it took is basically, instead of running each phase as a phase, we run it as an overlap. So everything is described with its concurrent movements. And that ended up being a lot. There were a lot of concurrent movements that could happen. So much so that we had to think outside the box, literally. The 332 cabinet on the left is what we traditionally use for traffic signals. It can only hold up to 18 outputs. Those are the actual outputs that run the signal heads themselves. With a design like this, we had to move on to a serial cabinet. That can do up to 32 different indications or groups of indications at the same time. One of the benefits here is that we get an updated conflict monitor, meaning if 2 green movements happen at the same time that shouldn't happen, the signal will go, okay, that's not supposed to happen, go into red flash. Now we can monitor things like conflicting yellows. Rather than wasting these circuit boards, these diode cards, we can just update the data key. So it's, again, a little bit better for our maintenance teams. And this is a picture of the back. So the wiring is pretty similar, but the nice thing here is you can pull out the terminals, do your wiring, plug it back in, rather than trying to fit a bunch of wires on one screw-in terminal. Okay, so that's a little bit about the design and operations. Now I want to just take a brief moment to talk about the unsung hero here. As we get into this conversation about TSP next, fiber really has become our backbone for our communication on this corridor. And again, we did something a little bit different, a little bit outside the box. So traditionally, fiber looks like it does on the left. We needed more fiber, more capacity for our communication system on this corridor. So we went with something called a ribbon fiber. And each one of these, it's hard to see again in the picture, but each one of these ribbons holds a certain amount of fiber strands. So it's a little bit more efficient packaging to get bigger capacity. And maybe this is a better view of it. But at the top, you see the 96 strand. And at the bottom, what we went with is a 432 strand. So 432 strands of fiber running along the corridor as the backbone. And you can see the sheathing on the left. They're about the same width and diameter, but you get a ton more capacity. And then I went to OMSI with my kids and I saw this and I thought this was interesting. So on the left, again, you see 3,000 pair or 6,000 copper wires running an old phone system. And on the right, 24 strands of fiber. And even at that size, it has over 300 times the capacity the fiber does than the old 3,000 pair. So this was huge because I'm talking about data collection. I'm talking about live access to our controllers. We need something like a fiber backbone to be secure, redundant, and accessible in order for us to be able to continue to respond to our communities. So now let's talk about transit signal priority. Who here knows what transit signal priority is? Okay, quite a few. Good. I'm gonna skip over a few of these things. You ever look up at a signal head and you go, what is that device? We can talk about that later. Here's a view of the radar detectors that I talked about that we're using. But I want to land on here. This is the Opticom receiver that's on almost every signal in the city. The Opticom receiver, the primary use of it is to provide preemption or the highest level of priority for emergency vehicles. Now, back in 1999, the city also developed what I call the legacy transit signal priority system. And it also used these line of sight detectors to provide priority for buses. Now, why don't we use preemption for buses? Why do we use priority and not the highest level priority, preemption? The OIR says that it dictates kind of what we can do and can't do with bus priority. And one of the main things is we can't change the sequence of the traffic signal controller. So it must maintain the sequence it usually has. And that means that if the bus approaches on a red, we can do everything we can to give it an early green without changing the sequence. If it arrives on green, we can give it a little bit more green time to get through that signal. And this was great for 1999. And this is kind of what it looked like on the street. So the bus is traveling along, it's kind of blasting an IRA at our signal saying, hey, I need priority. And the signal is doing its best to react to that input. Now this is line of sight, so it's maybe 300, 600 feet. And one of the challenges here, maybe a benefit, if you will, depending on how you ask the question, but one of the challenges for me as an operator is I only know what's happening on my side of the system. And even back then, I barely knew. I didn't have remote access. I didn't have the data streams I have now. And TriMet really knew what was happening with the bus, but they didn't really know what was happening with the signal system. Was the benefit happening for the bus? Were they getting their TSP? We went through an RFP process and decided regionally as on a vendor, and their name is Light. They provide cloud-based transit signal priority, and they really developed a bridge between our two systems. Again, one of the challenges with that is when you integrate new systems, sometimes you run into other things that you didn't expect. So their system relies on a Maestro device, like a little Apple TV, if you will, or Raspberry Pi size. That fits on our network, and we didn't like that. It's connected to the internet, and it's sitting on our closed network. So what we had to do was develop a tunnel. We created our separate VLAN. We run it through an entirely different firewall and try to separate and tunnelize that data stream as much as we can. But it does provide quite a few benefits. So now the bus is talking through Light. It's going through a machine learned predictive ETA model that then sends an ETA check-in and check-out to the next 3 signals in a row. So we're not now limited to 300, 600 feet away. We know when the bus requires a green with high certainty. This is also great for near side stops because that ETA is built into that near side stop. And here's kind of what it looks like from visually. The purple line represents the normalized ETA that we're receiving. The orange line is the speed of the bus, and the white dots are the bus stations. You can also see the signals there are integrated into the ETA. So we're getting ETA station to station and also signal to signal. Now, when we got the vendor, we had the design, we thought about operations. Now it's time to look at the controller. What can the controller do for us for TSP? And this is really the main page for the controller. It doesn't have a lot on here, and we can't use skip phases or skip PED in Oregon. So we did a bunch of testing to see what this would offer, and it often looked a lot like the legacy system. So the bus would get a green extension even if it was 2 minutes away, and the bus or the signal would hold the green a long time and then terminate right when the bus approached. So right when it needed its service, it would get a yellow or red. And since I believe that TSP is only good if it actually serves the people who ride the bus, I wanted to make it better. I wanted to give priority to people crossing, accessing their station before the bus arrives, rather than seeing their bus leave and waving at it. So I developed my own user programs around transit signal priority, and this is a lot to look at, and there's several of these, so I won't go through that. But I will show this. This is a flow chart kind of describing what it looks like and what's happening. And all I really want you to pay attention to here are 2 things. There's sort of a primary interval and a secondary interval. The primary in purple is really saying, okay, I know the bus is far enough away that I can do something at the signal to provide priority to people crossing the street, priority to other modes before the bus requires its green. So that's really what the purple section is doing. The blue section is saying the bus is close enough now, let's hold the phase. Let's not wait for a timer to elapse or something else in the controller. Let's actually control that and base that on the ETA we're receiving. So what does that look like? Here, and bear with me, I put these animations in PowerPoint, so they're as good as I could do. Here's the bus, it's approaching. It's greater than 120 seconds away, so we're saying don't accept information about that bus. It's also maybe greater than 3 signals ahead, so again, TSP is inactive, the bus is just traveling along. As it gets closer within that 2-minute ETA, now it's checked into our controller, and our controller is saying, okay, I see you, I'm going to start reacting to what's happening. As the bus approaches, it gets into that purple zone. So we know it's far enough away. We know enough about how our signal is operating. We can do something like provide PED priority, get people to their near side station, so that way they can actually access the bus as it's approaching. Now the bus is a little bit closer, and this picture doesn't do a good job, but maybe it's actually serving the stop, and that's included in the ETA. So we want to kind of be in a holding pattern, be in a place in this phase diagram where we're right before that bus opportunity in the phase diagram. And we hold the signal horizontal bar or red. We don't want to provide an early green for the bus. Now the bus has served the station, everyone's on the bus, everyone's off the bus that needs to be off. The bus has gotten close enough, the ETA is now less than 15 seconds. We're using that as the input to really activate the signal. So now we want to hold it in that bus phase and provide a vertical bar or a green for the bus. As the bus goes through, it actually checks out from light, or we manually check it out through a user program. And we give it a flashing triangle. Yep, it's flashing. And a horizontal bar. Now that all could have taken a while. That could have taken 45 seconds. And people who aren't riding the bus, they need to get across the street too and go on with their lives. So after the bus leaves, I provide another opportunity for PED priority for people to get across the street and go on their way. So all of this was sort of outside of the controller, what the controller features allow me to do. And so I wanted to make sure we tested it. And we did a lot of testing in the shop, testing in a testing environment. We got Light out here to do a preview of their system. We finally started testing at one intersection in the field. And then we got on the bus and we tested the entire corridor. So Light was on the bus, PBOT was on the bus. We were traveling through these signals as they were receiving that ETA up to 3 signals ahead, up to 120 seconds away. And now I want to show you what a bus signal looks like as you go through. Let's see if this works. So here we're waiting for the red, we're waiting for the vertical bar, people are moving along. There it goes, vertical bar, and the concurrent right turn only signal goes. You can also notice the concurrent left turn signal goes. Someone runs the red when they're not supposed to, right in front of the bus, and don't worry, the person on the scooter stops. But you get a queue jump type operation that way. And that's all run on the ETA. There's no other input that's activating it. And then I also want to show this video from TriMet to just show showing the bus going. You notice it stops at some locations where it's going to stop, or there's a non-detection issue like 130. But generally it makes it through. There's the vertical bar again. It makes it through almost everything. Oh, there is one in the middle run by ODOT. They use a different set of policies, so the bus does wait. You can also see the bus kneel down a little bit for each station that it serves. Signal. Stop it there, but yeah, this is a really cool. You can find it on YouTube. It goes through the whole corridor.
Is there an east one as well?
Not that I know of. Okay, so that was a sort of a preview of what it looks like from the bus perspective. This is another visual that I get as an operator. So anyone who has access to this now, like I talked about before, I can see what's happening with each bus as it approaches. TriMet can see the signal phasing as the bus approaches. So we're kind of connecting the two systems now through this portal. So that's really helpful for us. And this is on the FX. I have an FX filter on here, but I can see every bus in the system now. So that's really great. Another thing I'll mention here is that we did an expansion after division. So you see down in Southwest Capitol, there are 3 signals connected. The inner Hawthorne-Madison couplet has 7 signals. And you see the one on the Hawthorne Bridge. This is another kind of huge benefit of this TSP system. So even though TSP isn't acting on that bridge signal, we're offering TriMet kind of a visual into our side of the system saying, okay, now the bridge has lifted, the Hawthorne Bridge has lifted, and now TriMet can make different business decisions about what they want to do with their bus. Do they want to reroute? Is it going to be long enough? Similarly, at 11th and 12th, at just south of Cooch, there's a heavy rail and a light rail crossing there. We give them insights into our system so they can build business rules around what they want to do about rerouting the bus. So this is a huge benefit, not just for signals acted on by TSP, but also signals in the system that the route goes through. I will also mention sort of one challenge with this is we have so much more visibility. We have all the data streams, we have all the cool graphics and the fun systems to play with. But what that means is that sometimes it's really easy to focus on being responsive to this system and ignoring the other systems that our communities depend on so heavily. So, while it's a huge benefit for the FX, I want to just caution that, pay attention to your other systems too and work to make those as good as some of these other ones are. So I'll talk a little bit about before and after results from the TSP side, and then I'll hand it back over to Jess. As part of this project, TriMet hired a third-party engineering team to do a before and after study. Now, it wasn't a clear before and after. It was after the project had been completed. What happened was we turned off the TSP system. Then we turned on just the light piece of the TSP system without the PBOT logic that I developed. And then we turned it all back on. And we kind of did a before and after study that way. So with the TSP system and the PBOT logic, reduced the travel time for 8.2, about 8 minutes round trip. So every day, if you saved 8 minutes, what would you do with that time? That's something I like to think about. Just with the TSP, just the light system alone, it reduced travel time for the bus about 5%. and then you add in the PBOT logic that I developed, and it increases that reduction to 10%. The on-time percentage improved from 65 to 76, and the headway improved from 53 to 67. Now, these next two I'm personally proud of. The PED bike delay with just the TSP alone, just the light system, not the PBOT logic, increased. But then once you add in the PBOT logic, it actually went back to a non-TSP scenario, as if nothing ever happened, as if we weren't benefiting the bus at all. When you add in that little bit of effort, think about the problem in a different way, you can improve all modes, not just the bus. Similar with motorist delay, split failures, those increase with just the TSP alone, but then you add in the logic that I developed, and that reduces back down to a non-TSP scenario. I talked a little bit about our TSP expansions, and those have seen a 50 to 75% decrease in red light delay, just for transit. Now, although we won't have probably the funding to do this sort of before and after for every TSP deployment, hopefully the FX deployments we will. But this is a nice benefit to the system too. We get that red light delay basically right away after deployment. So we can see the benefits for transit pretty clearly after we deploy the TSP system. Now I'll hand it back to Jesse.
Thank you. Okay, so thanks for that dive into transit signal priority, Mark. We're going to zoom back out a little bit and share a little bit about what we now know about the project, being that we've been open for a couple years. So Mark had mentioned some of those travel time improvements we've seen. This is a bit older data, but what we're seeing is in different segments of the corridor, travel times for the bus really being on mark, if not exceeding those expectations that we had during planning phase of the project. If you remember earlier in the presentation, I mentioned we were really hoping for somewhere around 15 to 20%, and we really exceeded that in some locations. And my sense is that we may be seeing some improved travel times even over this, since some of this data was collected. It's also important to remember that we opened during the pandemic, and we've seen as a system our ridership go down quite a bit because of the pandemic. But post-pandemic, we've seen ridership on FX2 on division go up 40%. That's a big jump over where we're seeing elsewhere in our system, which is around 15%. We're continuing to see ridership increase on the line. So it's a really good sign that this service is performing well, that it's attracting riders, that it's really ultimately serving what we want it to, which is to get people to their destinations quicker and more reliably. With these projects, we also have opportunity to leverage them to do something more. When we look at transit projects like this, when it comes with federal funding, we are hyper-focused on the transit investment. We have to be, but we also recognize that there's opportunities to partner with PBOT, to partner with others regionally to deliver something more than just the transit investment and really set the table for improvements for the community. So in the case of FX2, we were able to do a lot in the way of improving crosswalks. If you remember, this was a high crash corridor, so safety was #1 priority. So being able to provide those safer pedestrian crossings, Mark had shown some of those predicted intersections that improve pedestrian environments significantly, able to do things like implement street trees, improve corridor lighting, partner with Metro and others to start being able to prime development for TOD to integrate affordable housing connected to transit. And again, improve overall safety and accessibility within a corridor where we were seeing fatalities and far too many crashes and incidents of harm. And then as a landscape architect, urban designer, I'm very proud of the opportunities we had to really improve the urban environment and to do things within the corridor that at the time people were really skeptical of. As we are in interdivision, if you've been there, you know that this is a very lively streetscape, and the sidewalk corridor is a place where people are out and eating dinner and having drinks. And there was a lot of concern about what a transit investment and big stations coming into that environment would look like. And so in our work, we really looked to understand what were those needs that they have, and how can our transit investments really build on some of the work that is already happening out there and really improve that urban environment. And if you go to a place like Ava Jeans or Loretta Jeans on a Saturday night in the summer, you can see that space blended between the existing sidewalk and now our transit environments are really one. And you can see people eating pie at our transit stops and really treating that as almost like an extension of that sidewalk space, almost like a mini plaza space. As we look ahead, we're looking to the next FX. And so I mentioned earlier in the presentation the high capacity transit plan that was developed in partnership with Metro. And so we've been really using that as a launching off point to look at what does it mean to have an FX system within our region, within the Portland region. If you go to other places like Minneapolis, Seattle, you'll see that there's a network of bus rapid transit, and we see a real opportunity in a network like this that better connects our community. And so our system plan that we're working on with our partners really looks to prioritize those corridors and really leverage those connections to better connect our community. So we're really early in that planning work. We just have a draft standards that we started to review this week, but we're really excited about rolling out FX beyond just division. So wanted to thank you for your time today. Happy to answer any questions with the time we have remaining. Anything else, Mark, that you had in closing? No? Okay. All right. Thank you all.
Thanks again, Mark and Jesse. For those viewing the webinar, please feel free to submit your questions using the Q&A feature in the control panel on the bottom of your Zoom window. Those in the room can raise their hands. We have about 13 minutes, so we'll try to split the questions evenly in time between in-person and online. And so we'll go ahead and start with in-person questions.
I was wondering, I noticed in the westbound ride through and also in the neat graphic that you did, there was quite a number of near side stops, and I was wondering in project development if y'all developed a a lost opportunity cost between the travel time savings from a near side far side stop versus a near side stop.
I'm not sure if there was a study that was done like that. I mean, I know that in the planning and design phase, we really looked closely at I mentioned earlier that we really wanted to be far side when we could to get through that intersection. But we just couldn't do that for multiple reasons. Sometimes we were just so constrained in a far side location, we just couldn't get a station there. And so being able to have queue jumps, have a receiving lane coming out of an intersection, those were also really important tools. And I know that the TSP and signal work that was done around some of those near side platforms were really helpful for us to, even if we couldn't stop far side, we could still get through those intersections more effectively.
I will say some of the signal design decisions were made before we knew who the TSP vendor was, before we knew we were going with a cloud-based transit signal party system. So, we got those queue jumps, we had a near side stop, and we did what we could at that time with our understanding to benefit the bus as much as we could. With the next gen TSP, the cloud-based TSP, that near side dwell time is built into the ETA that we're receiving. We're running that bus signal, that bus party phase on that ETA. So it says 30 seconds, even if it's right at the station, right at the signal. We're delaying that bus call until it's really ready. And that's kind of what the graphic was about.
Thank you for your presentation. I have to say I really love FX2. I use it just as a transit nerd. I just get in and just travel, and I don't have anywhere to go. And so having said that, I wonder, I think Jesse, you talked about it in the planning that began from 2014. I wonder if at the beginning, and also for future FX projects, did you thought about having the route completely dedicated bus lane, as BRT is technically defined as complete route in, I know because of where it is, right, it could be difficult. But I wonder if it was considered at the beginning of the planning stage for division. And for future effects, are you considering having a dedicated complete BRT throughout the whole network?
Yeah, thank you for bringing that up. We didn't really dive into it in terms of that toolbox of things we looked at for improving service. Lane dedication is also a really important tool in that toolbox. So there are some segments within division, I'm sure you know as a rider, that like in between 112th and 122nd, we have that lane, a business access transit lane. It is especially in a place like division where we are so constrained. Trying to get full lane dedication is really difficult, and there's a lot of trade-offs that are associated with that. We're looking at 82nd Avenue right now, and the work that we're doing is really understanding what does it mean to have segments of lane dedication within that corridor? What does it mean for future traffic congestion? Because, you know, we found and in those scenarios where we can't get 100% lane dedication, if we're doing something that slows down traffic enough, our bus in some cases wouldn't, it delays them as well before they can even get into a dedicated space. So we need to think really carefully about all of those trade-offs as we implement that tool. But it is a really important tool in the toolbox, and in corridors like this where we're so constrained, it's really difficult to get that full 100% lane dedication, but it is an important tool that we continue to look at in all of the corridors that we'll evaluate for FX.
I had two questions, one for each of you. For Jesse, in the beginning, when you were mentioning the bike lane configuration, I was just curious, was there ever like any consideration to do like sort of like a bend out where it went behind the platform? And if so, why was that not considered? I'm curious. And then for Mark, I mean, since we've been talking about the you know, the new FX line that's going to go on 82nd, I've seen this presentation before in the past. You've talked a lot about the logic of when, or you know, the issue when there's two buses coming from opposite directions and how the signal deals with that. But with the new FX line on 82nd, there's the opportunity for up to 4. And I was wondering if the logic now as it is will be good, or if there will need to be updates, or you know what that looks like.
I'll speak just real quickly. Also a great question that we didn't get a chance to really dive into, but the preferred alternative certainly for PBOT is an island station configuration where you can circulate bikes behind a station platform. Again, it came down to space. Typically from face of curb to back of walk, we had something like about 17 feet of space. Not nearly enough space to do an island station configuration that would meet all the needs in terms of pedestrian through zone width, in terms of a station width, and ultimately a bike lane. So that's really what ended up getting us to that station design. It was something that could work alternatively in such a tight space.
Yeah, and I will say eastbound 122nd, we did have enough space. So if you're looking for an example of what that looks like.
Yeah.
But yeah, your question about perpendicular FX routes. Yeah, that's going to be a big piece of the 82nd FX project. Is we're not just developing, I mean, right now, TSP is unlimited for every bus that goes through. The business rules are set up. There aren't really any business rules set up because I want to keep it unlimited so we get the benefits of the schedule as much as we can. I've done some local stuff with the controller to negotiate 2 buses approaching at the same time. But as perpendicular routes come through, I think we'll have to think about maybe more global business rules for the system.
Right, we're gonna take a couple of quick online questions, and if there's still time, we'll go back to in-person. Have there been any unexpected operations, maintenance costs, or maintenance costs for providing a next-gen TSP system?
Do you want to talk about this TriMet have?
I'm unaware. I'm sure there are. I'm not the best to speak to it, so I'll talk about it.
Yeah, for PBOT, anytime you integrate systems, in this case, third-party systems too, you'll run into issues, you know, and I think for the first 9 months, maybe 12 months after deployment, we were constantly reviewing the systems, making sure they were integrating correctly. You know, then you get a new controller version that you have to look at. Does that work and function the way you expect it to? New technology comes in all the time, and we're evaluating that. So I think that was sort of something that we ran into. And then anytime we have an issue at a signal, sometimes it's like, well, turn off the bus. The bus did that. So it's about navigating that space too and saying, was it really the bus or was it something else? And that takes more time and resources too. So I think as far as maintenance for physical hardware, because everything's brand new, we haven't had a lot of those issues, but it's really about the system side.
And I'll just mention, just generally speaking, is that there is maintenance of this system, right? And so I think that's conversations that as partners we're currently in is understanding and having a relationship and an agreement around who maintains and to what extent long-term.
The next question on here is about a specific application at a specific location. So has there been any ability to use the next gen TSP and logic routines to smooth out or address conflicts between FX and the railroad crossing at Southeast 12th Avenue?
So because the heavy rail is heavy, and they're the railroad, they actually get priority, they get preemption, so they get the ultimate priority at a signal. So the interaction between a bus that's being prioritized and a heavy rail vehicle, the heavy rail vehicle is going to override the priority. So we haven't implemented TSP at those locations yet. We have done other things, like I mentioned, where the TSP system is being leveraged to give information to TriMet, so TriMet can reroute their buses.
We had also invested as part of our Orange Line funding, made some improvements with UPRRR in their switching yard. It used to be a manual switch, and so conductor would get out, have to manually switch, probably have a cigarette, all the while the train's sitting there. And so we were able to make some improvements with the railroad to be able to make those improvements to help the bus a bit, but TSP.
Yeah, I was part of the evaluation of the older kind of TSP system, and one of the things that was happening before, like when you mentioned some impressive performance measures, and when there was congestion, really the TSP had a very hard time working because the queues were long and the extension of the early game were not enough. So I was just wondering, like those minutes of savings, if you have any breakdown between congested and uncongested times in terms of how it's working. I have another question. So it's kind of related to that. Like, have you seen with the right turns conflicting or delaying sometimes the bus operation? And the other one is in the estimation of the arrival. Sometimes what we had noticed, like when there was wheelchair access and the lift activation, that kind of, it was like could be 40 seconds to 2 minutes. And how is that taken into account in the way you guys are operating now? I mean, I know there are a lot of technical and one stuff, but
those are really great questions. The first one I'll answer. The traffic congestion, I sort of think of it as that's really something inherent whether the bus is there or not. And so we really should be taking care of that with the tools that we use for general traffic. The TSP can help a little bit because the ETA is machine learned. It knows Wednesday on a 2 p.m. there's a certain amount of traffic, so ETA will adjust. We use that ETA to really respond to the bus and have the signal respond to the bus. So we can do things like that. I mentioned the sort of secondary interval piece of my logic. That's really overriding what the controller wants to do and saying the bus is going to take 20 seconds instead of what you think 15. Let's hold the signal for 20 seconds, and that clears out any queue in front of the bus so the bus can access its station. So there was some thought put into the congestion as we did that. Specifically for the before and after study, that looked at AM and PM peak hours. So some of those numbers you saw are during the peak hours, which when we would expect most congestion. Second question, remind me.
the right turn.
The right turn. So similarly, the right turn is phased with the bus signal usually. And so what we're doing is we're saying, okay, the bus is coming. It's 70 seconds away. I know I can serve that conflicting ped bike movement, terminate that in time to get to that right turn signal. And so really with the addition of this user programming, we're seeing that the right turn is basically always up in time for the bus. If the right turn signal isn't on, the bus signal isn't on. And then as far as like ramp down or kneel down type operations, That is also all built into the ETA. So when someone pulls a cord, the ETA updates. When someone needs a ramp deployment, that's all being updated through the bus system, which is communicated to Light, communicated to us through the ETA.
Awesome. Thank you all for attending today's Friday Transportation Seminar. For those of you joining remotely, after the seminar ends, you'll have the opportunity to complete a brief survey about today's event. It only takes a few minutes to complete, and we would really appreciate your feedback. Thank you again, Mark and Jesse, and thank you all for joining us today in person and online.